What does the future hold, and how do you stay ahead? Artificial intelligence and machine learning for edge computing offers a clear-eyed look. We will focus on what it says about learning and algorithm. Stay with me, the best part is near the end. Chapter 1: Supervised Learning. Abstract 1, Introduction 2, Perceptron 3, Linear Regression 4, Logistic Regression 5, Multilayer Perceptron 6, KL Divergence 7, Generalized Linear Models 8, Kernel Method 9, Nonlinear SVM Classifier 10, Tree Ensembles References. Chapter 2, Supervised Learning, From Theory to Applications. Abstract 1, Introduction 2, What are regression and classification problems? Learning algorithms 4, Evaluation metrics 5, Supervised learning to detect fraudulent credit card transactions 6, Supervised learning for handwriting recognition 7, Conclusion references. Chapter 3, Unsupervised Learning. Abstract 1, Introduction 2, K-means clustering 3, K-means plus clustering 4, Sequential leader clustering 5, EM algorithm 6, Gaussian mixture model 7, autoencoders 8, principal component analysis 9, linear discriminant analysis 10, independent component analysis references. Chapter 8, Trust discovery and information retrieval using artificial intelligence tools from multiple conflicting sources of web cloud computing and e-commerce users. Abstract Acknowledgements 1, Introduction 2, Trusted Computing 3, Problem Identification 4, Truth Content Discovery Algorithm 5, Trustworthy and Scalable Service Providers Algorithm 6, Efficient Feature Extraction and Classification, EFSC, Algorithm 7, Query Retrieval Time, QRT, 8, Trust Content Discovery and Trustworthy and Scalable Service Providers Algorithm 9, Efficient Feature Extraction and Classification, EFEC, Algorithm and Customer Review Datasets 10, Summary 11, Conclusions 12, Future. Enhancements References. Chapter 9, Reliable Diabetes Mellitus Forecasting Using Artificial Neural Network Multilayer Perceptron. Abstract 1, Introduction 2, Related Works 3, Methodology 4, Building the Diabetic Diagnostic Criteria 5, Evaluating the Diabetes Outcomes Using Classification Algorithms 6, Conclusions References. Chapter 11, Integrating AI in E-Procurement of Hospitality Industry in the UAE. Abstract 1, Introduction 2, Problem Statement 3, Author's Contributions 4, Significance of the Study 5, Theoretical Framework 6, Research Aims and Objectives 7, Literature Review 8, Major Findings 9, Discussions 10, Major Gaps in the Study 11, Conclusions References. Chapter 12, Application of Artificial Intelligence and Machine Learning in Blockchain Technology. Abstract Acknowledgement 1, Introduction 2, Applications of Artificial Intelligence, Machine Learning, and Blockchain Technology 3, It Takes Two to Tango, Future of Artificial Intelligence and Machine Learning in Blockchain Technology 4, Edge Computing, A Potential Use Case of Blockchain 5, Conclusions References. Chapter 13, Implementing Convolutional Neural Network Model for Prediction in Medical Imaging. Abstract 1, Introduction 2, Convolutional Neural Networks 3, Implementing CNN for Biomedical Imaging and Analysis 4, Architecture Models for Different Image Type 5, Conclusion 6, Future Scope References. Chapter 15, Vehicle Telematics, an Internet of Things and Big Data Approach. Abstract 1, Introduction 2, Big Data 3, Big Data with Cloud Computing 4, Internet of Things, IoT, 5, Vehicle Telematics 6, Case Study Vehicle Reaction Time Prediction 7, Conclusions References. Chapter 16, Evaluate Learner-Level Assessment in Intelligent E-Learning Systems Using Probabilistic Network Model. Abstract 1, Introduction 2, Related Work 3, Contribution of Intelligent E-Learning System Using BN Model 4, Learner Assessment Model 5, Results and Discussion 6, Conclusions and Future Work References. Chapter 22: Hybrid Deep Learning Neurofuzzy Networks for Industrial Parameters Estimation. Abstract 1, Introduction 2, Preliminaries 3, Methodology 4, Results and Discussion 5, Validation of Model 6, Discussions on Performance Evaluation 7, Conclusions 8, Future Scope References. Chapter 24, Edge Computing, A Soul to Internet of Things, IoT, Data. Abstract 1, Introduction 2, Edge Computing Characteristics 3, New Challenges in Internet of Technology, IoT Edge Computing 4, Edge Computing Support to IoT Functionality 5, IoT Applications, Cloud or Edge Computing? Benefits and Potential of Edge Computing for IoT 7, Use Case, Edge Computing in IoT 8, Pertinent Open Issues which require additional investigations for Edge Computing 9, Conclusions References. Chapter 25, 5G, the Next Generation Technology for Edge Communication. Abstract 1, Introduction 2, History 3, 5G Technology 4, 5G Cellular Network 5, Components used in 5G Technology/Network 6, Differences from 4G Architecture 7, Security of 5G Architecture 8, 5G Time Period 9, Case Study on 5G Technology 10, 5G Advancement 11, Advantage and Disadvantage of 5G Technology 12, Challenges 13, Future Scope 14, Conclusions References. Chapter 26, Challenges and Opportunities in Edge Computing Architecture Using Machine Learning Approaches. Abstract 1, Introduction 2, Overview of Edge Computing 3, Security and Privacy in Edge Computing 4, Intersection of Machine Learning and Edge Using Enabling Technologies 5, Machine Learning and Edge Bringing AI to IoT 6, OpenVINO Toolkit 7, Challenges in Machine Learning and Edge Computing Integration 8, Conclusions References. Chapter 27, State of the Art for Edge Security in Software-Defined Networks. Abstract 1, Introduction 2, Hybrid Software-Defined Networks 3, Security Challenges in Hybrid Software-Defined Networks 4, Solutions for Hybrid Software-Defined Networks 5, Learning Techniques for Hybrid Software-Defined Networks 6, Discussion and Implementation 7, Conclusions References Further reading. Chapter 28, Moving to the Cloud, Fog, and Edge Computing Paradigms, Convergences in Future Research Direction. Abstract 1, Introduction 2, Features and Differences between Cloud, Fog, and Edge Computing 3, Framework and Programming Models, Architecture of Fog Computing 4, Moving Cloud to Edge Computing 5, Case Study, Edge Computing for Intelligent Aquaculture 6, Conclusions References. Chapter 30, AI Cardiologist at the Edge, a use case of a Do Computing Heart Monitoring Solution. A use case of a Do Computing Heart Monitoring Solution. Abstract 1, Introduction 2, Related Work 3, Architectural Approach 4, E.C. Gallert Use Case 5, Discussion 6, Conclusions References. Chapter 1, Supervised Learning. Kanishk Tyagia, Chinmay Ranab, Michael Manrica Aptiv Advanced Research Center, Agora Hills, California, United States. Quantifi Incorporated, Marlborough, Massachusetts, United States. Department of Electrical Engineering, the University of Texas at Arlington, Arlington, Texas, United States. Abstract machine learning models learn different tasks with different paradigms that effectively aim to get the models better through training. Supervised learning is a common form of machine learning training paradigm that has been used successfully in real-world machine learning applications. Typical supervised learning involves two phases. In Phase 1, commonly called training, we give input and expect output, also known as ground truth, and train a model with respect to a metric using an optimization algorithm. In Phase 2, commonly called testing, we deploy the model with unseen data and expect it to either classify or approximate the outputs. Although supervised learning is covered in almost all machine learning textbooks, we will introduce and explain supervised learning from an application point of view and its relationship to edge computing. All the algorithms will be explained from a mathematical and theoretical point of view and a programmer's perspective. This will help in doing hands-on experience in implementing algorithms for a variety of problems. Keywords: linear regression, logistic regression, steepest descent, conjugate gradient, multi-layer perceptron, second-order algorithms, KL divergence, generalized linear models, kernel machines, bootstrapping. 1. Introduction. This chapter discusses various supervised learning paradigm that is used to train and deploy machine learning models. While the theory on supervised learning is predominated mainly by the computer vision and natural language processing community, much research is required in its application to edge computing. With the recent advances in machine learning algorithms, combined with the increasing computational power, edge computing is another area of application where machine learning will be improving the current technology. According to a white paper from Cisco, 50 billion Internet of Things (IoT) devices will be connected to the Internet by the end of 2020, and even though the estimation that nearly 850 ZB of data will be generated per year outside the cloud by 2021, the global data center traffic is only 21 ZB approximately. This means that a transformation from bug cloud data centers to a wide range of edge devices is happening. We plan to cover the traditional supervised learning algorithm basics and the trade tricks while implementing them for various real-life applications. The assumptions made and the programming decisions made while implementing them are also discussed. We start with generalized linear models along with optimization algorithms, gradient descent, Newton-S method, and metrics, mean square error, MSE, cross-entropy, used in training the model. Then, NaVe Bayes and kernel methods are discussed along with the decision tree and its variants. We provide pseudocode for all the supervised learning algorithms that we discuss to give the readers an idea of how the algorithms are implemented from theory to practice. In addition, supervised learning algorithms that capture the variation of input data distribution and algorithms that project data in higher subspace and first and second order learning paradigms are the subject matter of this chapter. The chapter covers the learning paradigms in sync with the modern day application to edge computing from an implementation perspective. Edge computing in machine learning will enable the devices to have a more pervasive and fine-grained intelligence. Supervised learning is a common way of training machine learning algorithms that can be later used in the inference stage on IoT and other edge devices. This chapter covers several supervised learning algorithms that are commonly used in various real-life applications. Covers the basic perceptron model that helps understand the learning algorithm. In Section 3, the linear regression algorithm is discussed that extends the idea of perceptron algorithm to solve supervised regression tasks. We discuss commonly used gradient-based learning algorithms along with their pseudocodes. Discusses logistic regression, which is a very commonly used classifier due to its simplicity in structure and generalizability. In Section 5, we bring the concepts together from the previous sections to discuss the multi-layer perceptron (MLP) network, a widely used neural network in real-life applications. We explain the structure, initialization strategy, and detail out various learning algorithms that are reused to train an MLP. Discusses the Kullback-Leibler (KL) divergence measure used to calculate how two probability distributions are different from each other. Discusses the generalized linear models that extend to the linear models but with a non-linear activation on the output nodes. Talks about the kernel methods leading to Section 9 that explains nonlinear support vector machine (SVM) classifiers. We conclude this chapter in Section 10 by discussing various tree ensemble algorithms. Perceptron algorithms came in early 1960. However, Minsky and Papert, 2, show the restriction they have. Rosenblatt, 3, described an alpha perceptron that is an example of a statistical pattern recognition (SPR) system. In a typical SPR system, the features are obtained from the raw input using no learning mechanism but instead using a common sense rule. Therefore, a human decides what is a good feature and sees if it works, and if it does not work, tries another. We learn the weight associated with each feature activation to get a single scalar quantity and then based on if this quantity is above or below a threshold. In a typical perceptron model for input vector, X is used to compute a weighted sum from all the neurons and added with a bias vector. This bias vector is also known as the threshold vector in the literature. 1. The linear perceptron will output Y depending on the following rule as shown in Fig. 2. The perception algorithm is fast and straightforward, and if the dataset is linearly separable, it is guaranteed to converge. Fig. 1. Perceptron activation functions. Linear regression. In this section, we discuss the structure and notation of a linear regression. As shown in Fig. 2. A linear regression is a weight matrix W that transforms an input vector X into a discriminate vector Y. 4. The weight W, M, N, connects the nth input to the mth output. The training dataset, XP, TP, consists of n-dimensional input vectors XP and m-dimensional desired output vectors TP. The pattern number P varies from 1 to NV, where NV denotes the number of training patterns. The threshold is handled by augmenting X with an extra element, which is equal to 1 as XA equals 1 XT, T. So XA contains new basis functions, where new equals n plus 1. For the pth training pattern, the network output vector, YP, can be written as 3, where ZAP denotes XA for the pth pattern. Fig. 2. Linear regression. Training a linear regression. To train the linear regression, we minimize the error function E that is a surrogate for a non-smooth classification error. As in Ref. 5, from a Bayesian point of view, we consider maximizing likelihood function or minimizing MSE in the least square sense, where the MSE between the inputs and the outputs is, 4, here, the target output for the correct output. M denotes the total number of outputs. We minimize the error function from EQ, 9, with respect to W by solving the M sets of n plus 1 linear equations given by 5, where the cross-correlation matrix C and the autocorrelation matrix are R, respectively, 6, 7, since R in EQ, 35, is often ill-conditioned, it is unsafe to use Gauss-Jordan elimination. EQ, 35, is solved using orthogonal least squares, OLS, 6. In Ref. 7, OLS is used to solve for radial basis function network parameters. OLS is useful for practical applications for two primary reasons. First, the training is fast since solving linear equations is straightforward. Second, it helps us to avoid some local minima. 8. In terms of optimization theory, solving EQ, 35, for W is nearly Newton's algorithm for the output weights, 9. Given, 8, and the error function, 9. Expanding on EQ, 9, 10, 11, doing a partial of error W, T weight W, 12, EQ, 12, equal to 0 leads to the following normal equation, 13. Since there is a matrix inversion in EQ, 13, the computation cost is roughly O, and 3, using a Gauss-Jordan elimination method. Therefore, normal equations are used only for a few thousand patterns, and with a more complex or higher-order equation, gradient descent-based algorithms are applied. 14, 15, steepest descent. The steepest descent gradient algorithm can be summarized in Algorithm 1. Algorithm 1 steepest descent gradient algorithm. Initialize W, nit, at 02, while at nit 03, calculate G from EQ, 12, 4, compute B2 from EQ, 15, 5, update W as W plus B2 G6, it plus 17, end while Fig. 3 illustrates gradient descent using a two-dimensional, 2D, contour plot. The x-axis denotes the first weight W1 and the y-axis is second weight W2. The arrows, G0, G1, G2, G3, G4, G5, in Fig. 3 determines the direction of the negative gradients for each of the weights to reach a minimum. The learning factor controls the step size derived in EQ. We can observe that gradients get smaller as they approach the minimal point. Fig. 3 Steepest descent 2D contour plot. From a programmer's perspective, some of the debugging steps are: 1. E is non-increasing. 2. EG approaches 0. 3. B20. Conjugate gradient. As we see from the previous section, the weights are updated in the negative gradient direction in a basic gradient algorithm. Although the error function reduces most rapidly along the negative direction of the gradient, it does not necessarily create fast convergence. Conjugate gradient (CG) algorithm 10 performs a line search in the conjugate direction and has faster convergence than the backpropagation (BP) algorithm. Although CG is a general unconstrained optimization technique, its use in efficiently training an MLP is well documented in RAF. To train an MLP using CG algorithm, we use a direction vector that is obtained from the gradient G as 16. Here, P equals vec, P, po, poi, and P, poi, and po are the direction vectors. B1 is the ratio of the gradient energy from 2 consecutive iterations. This direction vector, in turn, updates all the weights simultaneously as follows. 17. CG algorithm has many attractive qualities such as the following. 1. The number of iterations it takes to converge is equal to the number of unknowns. It performs better than steepest descent, and it can be applied to non-quadratic error functions. Since there is no Hessian involved, we do not invert any matrix, and the computational cost is O, W, where W is the size of the weight vector. The CG algorithm can be summarized in Algorithm 2. Algorithm 2 Conjugate Gradient Algorithm. Initialize W, nit, it 02, while at nit 03, calculate P from G4, compute Z from EQ, 15, 5, update W as W plus ZP6, it plus 17, end while Fig. 4 illustrates CG using a 2D contour plot. The x-axis denotes the first weight W1 and the y-axis is second weight W2. From the plot, we can observe that CG needs n plus 1 number of steps to reach the minimum. Fig. For conjugate gradient 2D contour plot. From a programmer's perspective, some of the debugging steps are as follows. 1. E is non-increasing if E is quadratic. Forcing B1 equals 0. This should result in a steepest descent algorithm. Calculate IP equals 4 every it. Logistic regression. The name for logistic regression is a misnomer since it is still a classification. A general two-class classification with posterior probability of one class being 18, 19, 20. Since it is a two-class classification, the classes C1 and C2 can be denoted as Y0, 1. Linear regression does not normally work in classification since even if Y equals 0 or 1, can be greater than or less than 1. Therefore, we use logistic regression in which Y0, 1. It should be emphasized that this is still a classification rather than a regression. Here is a logistic function defined as 21, when WTX tends to then tends to 1 and when WTX tends to then tends to 0. The decision boundary for logistic regression is the property of the parameters and not the training set. So, if there is a nonlinear decision boundary, it is mapped according to the nonlinear activation function used in logistic regression. Since is nonlinear, sigmoid, the decision boundary can be learned as manifold learning of nonlinear surfaces. In order to train the logistic regression, the cost function J, W, should preferably be convex so that only one global minimum is present. We would not use the MSE as in linear regression since it is a non-convex function with multiple local minima. However, there are ways to train a logistic regression along with MSE 12, 13. The logistic regression cost function will be as follows. 22, EQ, 22, comes from maximum likelihood estimation, MSE. To fit parameter W, we minimize J, W. Once the training is completed, the prediction for new input X is given as 23. In order to get G, we do the following calculations by chain rule: 24, 25, 26, 27, therefore 28. In order to train, we minimize J, W, using gradient descent algorithm as in algorithm 3. Algorithm 3 is a fundamental building block for more advanced algorithms like CG, BFGS, or LBFGS. Algorithm 3 Gradient Descent Algorithm. Initialize W, NIT, at 02, while at NIT03, calculate G4, update W as W plus ZG5, at plus 16, end while, softmax classifier. The softmax classifier, 5, is a generalized logistic regression classifier that outputs approximate class probabilities. Structurally, it is a linear model with softmax function, 14, at the output units. For the pth pattern, it maps the input vector xp to the output class labels as 29, where W is a weight matrix. The performance measure is a cross-entropy loss function, 5, as 30. The softmax classifier is often trained using LBFGS training algorithm, 15. Multilayer perceptron. In this chapter, we start by describing the multilayer perceptron, MLP, a nonlinear signal processor with good approximation and classification properties. The MLP has basis functions that can adapt during the training process by utilizing example input and desired outputs. An MLP will minimize an error criterion and closely mimic an optimal processor in which the computational burden in processing an input vector is controlled by slowly varying the number of coefficients, 16, 17. We review the first and second order training algorithms for MLP, followed by a classifier design of MLP through regression. Structure and notation. Fig. 5 illustrates a single-layer fully connected MLP. The input weights W, K, N connect the nth input to the KTH hidden unit. Output weights WO, M, K connect the KTH hidden unit S nonlinear activation up, K, to the MTH output YP, M, which has a linear activation. The bypass weights Y, M, N connects the nth input to the MTH output. The training data described by the set of independent identically distributed input-output pair consist of n-dimensional input vectors xp and m-dimensional desired output vectors tp. The pattern number p varies from 1 to nv, where nv denotes the number of training vectors present in the datasets. Let nh denote the number of hidden units. In order to handle the thresholds in the input layer, the input unit is augmented by an extra element xp, n plus 1, where xp, n plus 1, equals 1. For each training pattern p, the hidden layer net function vector np can be written as 31. The kth element of the hidden unit activation vector op is calculated as opk equals f, np, k, where f denotes the sigmoid activation function. The network output vector yp can be written as 32. The expression for the actual outputs given in EQ, 32, can be rewritten as 33, where xa equals xpt opt, t is the augmented input column vector with new basis functions, where new equals 1 plus n plus nh. The total number of weights nw equals nh, 1 plus n, plus mnh. Similarly, Y is the m by new-dimensional augmented weight matrix defined as W equals WO. Fig. 5 fully connected MLP. To train an MLP, we recast the MLP learning problem as an optimization problem and use a structural risk minimization framework to design the learning algorithm. 5.18. Essentially, this framework is used to minimize the error function E as in EQ 9, that is a surrogate for a non-smooth classification error. As in Ref. 5, from a Bayesian point of view,
We consider maximizing likelihood function or minimizing MSE in a least square sense.
Therefore, the MSE between the inputs and the outputs is defined as 34, here, is an L2 regularization parameter used to avoid memorization and overfitting. The nonlinearity in YP causes the error E to be non-convex, and so in practice, local minima of the error function may be found. In the earlier discussion, we have assumed that TP has a Gaussian distribution with input XP. In case the conditional distribution of targets, given input has a Bernoulli distribution, the error function, which is given by the negative log likelihood, is then a cross-entropy error function, 5. In Ref. 5, it is concluded that using a cross-entropy error function instead of the MSE for a classification problem leads to faster training as well as improved generalization. Apart from cross-entropy in L2 error form, we also have an L1 error measure.
Golick et al., 19, and Samar et al.
20, discuss a good comparison between the L2 and cross-entropy and suggest using cross-entropy error function for classification in order to have faster training and improved generalization. Our goal is to obtain an optimal value of the weights connected in an MLP.
In order to achieve this, we use empirical risk minimization, 17, framework to design the learning algorithms.
An essential benefit of converting the training of an MLP into an optimization problem is that we can now use various optimizing algorithms to optimize the learning of an MLP. Initialization, input means and standard deviations. If some inputs have even more significant standard deviations than others, they can dominate the training, even if they are relatively useless. Inputs are normalized with zero mean and unit standard deviation. Randomizing the input weights as from Manry, 16, the input weights matrix W is initialized randomly from a zero-mean Gaussian random number generator. The training of the input weights strongly depends on the gradient of the hidden unit S activation functions with respect to the inputs. Training of input weights will cease if the hidden units it feeds into have an activation function derivative of 0 for all patterns. In order to remove the dominance of large variance inputs, we divide the input weights by the input S standard deviation. Therefore, we adjust the mean and standard deviation of all the hidden units' net functions. This is called net control as in Ref. At this point, we have determined the initial input weights, and we are now ready to initialize the output weights. To solve for the weights connected to the output of the network, we use a technique called output weight optimization, OWO, 22-23. OWO minimizes the error function from EQ, 9, with respect to A by solving the M sets of new equations given by 35, here, the cross-correlation matrix C, autocorrelation matrix R, 36. In order to incorporate the regularization, we modify the R matrix elements except the threshold is 37, where R is a vector containing the diagonal elements of R and diagram, is an operator that creates a diagonal matrix from the vector. The MLP network is now initialized and ready to be trained with first or second order algorithms. Training in MLP can be seen as an unconstrained optimization problem that usually involves first-order gradient methods such as BP, CG, and second-order Levenberg-Marquardt, LM. Newton S method is the most popular learning algorithm. Training algorithms can be classified as one-stage algorithm, in which all the weights of the network are updated simultaneously. Two-stage algorithm, in which input and output weights are trained alternately. Fig. 6 shows a flowchart that summarizes all the training algorithms that will be described in the subsequent sections. Fig. 6 typical training algorithms for training in MLP. First-order learning algorithms. The first-order learning algorithms update the weights of the MLP based on gradient matrices, that is, the first-order information, hence the name. We start by discussing the training of an MLP with a one-stage algorithm. In this, we train both the output and input weights simultaneously using either BP or CG algorithm.
We then describe a two-stage algorithm called OWO hidden weight optimization.
Backpropagation algorithm. The BP algorithm is a greedy line search algorithms that have a step size to achieve the maximum amount of decrease of the objective function at each step. 5. BP is a computationally efficient method in conjunction with gradient-based algorithms that are used widely to train an MLP. 24.
However, due to the non-convexity of error function (EQ) in neural networks, BP is not guaranteed to find global minima but rather only local minima. Although this is considered as a major drawback, recently in Ref. 25, it is discussed as to why local minima are still useful in many practical problems.
In each training epoch, we update all the weights of the network in a BP algorithm as follows. 38. Here, W is a vector of network weights as W equals vec, W, wo, woi, and G is a vector of network gradients G equals vec, G, go, goi. The gradient matrices are negative partial of EW, T the weights, and vec operator performs a lexicographic ordering of a matrix into a vector. Z is the optimal learning factor that is derived using a Taylor series expansion of the MSE, expressed in terms of Z, as 26, 39. The BP algorithm can be summarized algorithm for
backpropagation algorithm.
Initialize W, nit, it 02, while at nit 03, calculate G4, compute Z from EQ, 39, 5, update W as W plus Z G6, it plus 17, and while as in Ref. 5, the BP algorithm has two major criticisms. First, it does not scale well, that is, it takes operations for sufficiently large NW, and second, being a simple gradient descent procedure, it is unduly slow in the presence of flat error surfaces and is not a very reliable learning paradigm. Training lemmas. Lemma 1 for the KTH hidden unit. If F, NP, K equals 0 for all patterns, then weights feeding into the unit will not change during BP training.
Proof.
Observe the partial derivative formula below. The partial of E with respect to W, K, N is 0 under the conditions of the lemma. 41. Note that F, NP, K is greatest for zero-valued net functions.
Implications 1.
It would seem then that zero-valued initial weights are a good idea, since F is largest for net values equal to 0. During net control, it seems that standard deviation should be less than 2 and mean should be close to 0.
Lemma 2. Let the KTH hidden unit have any set of weights.
Let units K plus J for J between 1 and K1 have identically valued input and output weights as the kth unit. In other words, W, K plus J, N is the same for J between 0 and K1, and wo, I, K plus J, is the same for J between 0 and K1. After training with BP, all K of these hidden units still have identically valued weights, and can be replaced by a single hidden unit.
Proof. If the units start with identical weights, they have identically valued weight changes and are still identical after training.
The hidden unit outputs start identical and may experience identical weight changes.
OWOBP is more difficult to predict. Implications. Random initial weights ensure that no hidden units are identical.
Lemma 3. During BP training, input weights are sensitive to input means.
Proof.
Modeling XP, N, as EP, N, plus Mn, where EP, N, is 0 mean and Mn is the mean of the nth input, the negative partial of E with respect to W, K, N, is found as 42. Note that as Mn increases, becomes dominated by the first term, which has no information related to changes in the nth input. Lemma 4. OWOBP will not change thresholds, K, or W, K, N plus 1, unless F, NP, K, changes with P. Proof. Assume F, NP, K, does not change with P. Hence, we get 43, lemma 5 an optimal MLP structure for the multi-output approximation case, m greater than 1, has different hidden units for each output. Proof. The input weight gradient matrix G is found as 44, updating the weights. The GI and learning factor differs for each output. The optimal MLP will have different hidden units with different input weights for each output.
Implications 1.
If the KTH hidden unit S activation has constant slope f, NP, K will not change during BP training. So, during net control, we should not have mean equals 0 and standard deviation too small. Together, lemmas 1 through 4 provide the motivation for zero mean inputs, random initial weights, and net control with mean and standard deviation 0.
Lemma 5 shows that if a multi-output MLP is trained, using the same hidden units for each output, it is not optimal. Lemma 3 shows that BP lacks affine invariance, 27.
Second-order learning algorithms. The basic idea behind using a second-order method is to improve the first-order algorithms by using the second derivative along with the first derivative, 5. We present two one-stage algorithms, namely Newton-S method and LM, and then a two-stage algorithm called as OWO multiple optimal learning factor, 2830. Newton-S method. For Newton-S method, given a starting point, we construct a quadratic approximation to a double differentiable error function that matches the first and second-order derivative value at that point. We then minimize this quadratic function instead of the original error function by expanding the Taylor series of E about the point Wk, as is clear from the equation below. 45. Here is the new version of W that we are trying to find. We calculate the Hessian ingredient, H and G of the MSE error function, where the elements of H are given by 46, and the elements of G are given by 47. We calculate the second-order direction, D, by solving the set of linear equations with OLS, 48, assuming quadratic error function in EQ, 9, and H to be positive definite. Applying first-order necessary condition, FONC, 31, on all the weights in an MLP, we update the weights as 49. The Newton-S algorithm can be summarized in Algorithm 5.
Algorithm 5 Newton-S algorithm. Initialize W, nit, at 02, while at nit-2 calculate G and H from X. 46, 47. 4. Compute D from EQ, 48. 5. Update W as W plus D6, it plus 17, and while Newton-S method is quadratic convergent and affine invariant, 16. Since it converges fast, we would like to use it to train an MLP, but generally, the Hessian H is singular, 32. If the error function is quadratic, then the approximation is exactly a one-step solution, otherwise the approximation will provide only an estimate to the exact solution. In case of a non-quadratic error measure, we will require a line search, and W is updated as 50. LM algorithm. The LM algorithm is a compromise between Newton-S method, which converges rapidly near local or global minima but may diverge, and gradient descent, which has assured convergence through a proper selection of step size parameter but converge slowly. Following EQ, 45, the LM algorithm is a suboptimal method. Since usually H is singular in Newton-S method, an alternate is to modify the Hessian matrix as in LM, 33, algorithm, or use a two-step method such as layer-by-layer training, 34. In LM, we modify the Hessian as 51. Here, I is the identity matrix of the exact dimensions as H and is a regularizing parameter that forces the sum matrix, H plus I, to be positive definite and safely well-conditioned throughout the computation. We calculate the second-order direction, D, similar to Newton-S method as 52. After obtaining HLM, weights of the model are updated using EQ. The regularizing parameter plays a crucial role in the way the LM algorithm functions. If we set equal to 0, then EQ, 52, reduces to Newton-S method, EQ.
On the other hand, if we assign a large value to such that I overpowers the Hessian H, the LM algorithms are effective as a gradient descent algorithm.
Press et al. 35 recommend an excellent Marquardt recipe for the selection of.
From a practical perspective, the computational complexity of obtaining HLM can be demanding, mainly when the dimensionality of the weight vector W is high. Therefore, due to scalability constraints, LM is particularly suitable for a small network.
The LM algorithm can be summarized in Algorithm 6. Algorithm 6 LM algorithm. Initialize W, NIT, IT02, while at NITO3, present all patterns to the network to computer error yield from EQ, 9, 4, calculate G and H from X. 46, 47, 5, obtain HLM from EQ, 51, 6, compute D from EQ, 52, 7, update W as W plus D8, recompute the error ANU by using the updated weights. 9. If ANU yield 10, reduce the value of 11, go to step 312, else 13, increase the value of 14, and if 15, it plus 116, and while 6, KL divergence from an information theory point of view, Kullback-Leibler, KL. Divergence is a relative entropy measure that estimates how close we have modeled an approximate distribution Q, X, with respect to the unknown distribution P, X. In order to arrive at the expression for KL divergence, we follow the probabilistic viewpoint. The following explanation is suitable for both continuous and discrete distribution. In order to quantitatively determine how good the approximate model Q, X, is compared to X, we calculate the log likelihood ratio for an entire dataset as 53, EQ, 53, represents that for any random sample X, how much likely is it that the data point is to occur in P, X, as compared to Q, X. An intuition behind EQ, 53, is that if P, X, fits the data more closely, then it will give a value greater than 0, whereas a value less than 0 indicates that Q, X, better fits the data. In case the models fit the data equally well, EQ, 53, will give a value of 0. So with EQ, 53, we can quantify how much better one model is better over the other given the dataset. For a large dataset with n sampled points that are independent and identically distributed, IDE, we calculate an analytical term called an average predictive power for n as 54. In other words, the expected value of log, or, is analytically defined as the familiar KL divergence expression, 55. The way the probabilistic interpretation is connected to the neural network design is the assumption of IDE.
A common misconception about KL divergence is to think of it as a distance between the P, X, and Q, X. However, this is wrong since KL divergence does not follow the commutative property, that is, KL, PEQ, KL, PEQ. Generalized linear models from Section 3 on linear regression, we add a nonlinear activation to the output neurons and create a class of models known as generalized linear models. Platt, 36, has shown the utility of using nonlinear output activations such as sigmoids.
We describe an algorithm that uses sigmoidal output activation to bound network outputs as shown in Fig.
The error of the resulting generalized linear classifier, GLC, is 56, where OP, I, is defined as F, YP, I, and F, denotes the sigmoid activation function. Fig. 7 Generalized linear model. In order to mitigate this increase in EG, we need to map the linear output activations YP to sigmoidal outputs OP as 57, where A and B are scalars that are found such that EG is minimized. Kernel method A second-order feed-forward training algorithm for a radial basis function, RBF, classifier is described in refs. Using a weighted measure between K cluster setters and input patterns, the RBF basis functions are given as 58, modifying EQ, 9, the RBF objective function is 59, where YP, I, is the ith element of the output discriminate vector, 60, equating the gradient of ERB, to 0, we solve for the output weight matrix using OWO 37. Let mk, k, and c, n denote the kth center vector, the kth spread parameter, and the weighted Euclidean distance measure weight for the nth input. These parameters are optimized using an efficient Newton-S algorithm. 37. Nonlinear SVM classifier. A nonlinear support vector machine (SVM) follows the structure similar to the RBF classifier. In a nonlinear SVM, k, xp, xq, xp, t, xq is called the kernel function and xq is a feature function. For our comparisons, 0. For a given two-class classification problem, a nonlinear SVM solves the following convex optimization problem. 61, subject to I0. Here, the weight vector y is NSV by 1 and b is a bias. The basis vector xp is NSV by 1 and 1p NSV. C is a user-specified positive parameter, and the p are called the slack variables. We need to find the optimum values of the weight vector w, bias b, and the slack variables p to minimize ESM. The coordinated descent algorithm, 39, is used for training. For multi-class problems, one versus the rest strategy is implemented. Tree ensembles, decision trees. Decision tree, 40, is an upside-down tree-like structure generated from training data with the main root at the top as shown in Fig. Each node is further split into subsequent nodes called branches/subtree depending on the decisions made using training data. The tree SN where the tree further does not split is the leaf/terminal nodes that indicate the final decision. Decision trees are used for both approximation and classification data. Fig. 8. Decision tree. A decision tree is learned by splitting the branches into subbranches depending on the lowest error values. The split decision for approximation data is made based on the variance of the node. The node with lower variance is used to split the decision tree further. The decision for classification data is made based on information gain, Gini impurity, or chi-square. For smaller decision trees, we use information gain as the higher the information gain purer the nodes are. For a feature A for NV number of samples, the information gain is given as 62. Here, we use entropy as we need to find a single variable's outcome as compared to the cross-entropy function used in EQ, 22, where we found the outcome of two variables. Entropy, NV, is defined as follows. 63. The best information gain feature is the best decision feature of the main root, and all other features follow the feature with the best information gain. One of the disadvantages of using a decision tree is that the more the number of features and fewer samples, the algorithm's complexity increases as the decision trees grow, leading to overfitting and high variance of the model. Overfitting can be avoided by using reduced error pruning. 41. Removing branches from a node, and setting the node as a decision leaf node depending on the performance. Decision trees are also more prone to changes in the data. A small change in the input data can have a drastic impact on the grown trees. To reduce variance in a statistical model, bootstrap aggregation or bagging is used. Bagging refers to creating multiple random copies of a training dataset, fitting a separate decision tree for each dataset, and finally averaging the final predictions to reduce variance, which will be discussed in section. Decision trees can be used in various applications as they can process both categorical and continuous output data. Decision trees usually do not require feature scaling as scaling does not affect the split decision made by a tree during training. Compared to neural networks, decision trees suffer from generalization. Decision trees cannot be trained online when the model has to be updated continuously, causing the decision tree to fail. The complexity of a tree is the longest route from the root node to the leaf node. Random forest. The random forest consists of a large number of different uncorrelated decision trees that predict its class.
Random forest uses bagging and bootstrapping along with multiple decision trees for each bootstrapped data.
Bagging refers to creating multiple random bootstrapped copies of a training dataset. Each of these individual trees has a high variance. Thus, to reduce variance, we take average of these indecision trees. For example, if we have 3 bootstrapped training datasets as shown in Fig. 9, then each of these random subsets is fitted with 3 decision trees, also called base learners, resulting in a total of 3 different predictions. The majority voting from these 3 predictions is used to produce final predictions. Fig. 9 Random forest. Similarly, we can do this for n sets of bagged decision trees to produce more stable and accurate models. The n sets of bagged trees can be highly correlated if there is a strong predictor in the dataset. As we use all of the predictors from the dataset, bagging will use a stronger predictor every time a tree is created, starting from the main node, causing highly correlated trees. However, in the case of random forest, the choice of predictors varies. During each split, the number of m predictors chosen is approximately equal to the square root of a total of p predictors. Thus, the splits will not always pick the strong predictor as the main nodes. These large number of uncorrelated trees perform better than bagging an individual decision tree. If m equals p, the random forest algorithm will work similar to bagging. Algorithm 7. Algorithm 7 Random forest. Create in bootstrap data, where n is the number of decision trees. 2. Build in decision trees using each of the bootstrap data. 3. For testing, fit a new data with all the indecision trees and get the output with most votes. From a programmer's perspective, 1. Random forest algorithms are robust to outliers and are most commonly used first-choice algorithms. Out of all the data, 1/3 data are never used during training due to bootstrapping, called an out-of-bag dataset. These out-of-bag datasets can be used as a validation set. Missing data can be handled in random forest by using proximity matrix, which means a measure of closeness or nearness between pairs of cases. Random forest can give features importance. As random forest uses bagging approach, each tree can be run parallel to each other to save time. Advantages of random forest over neural networks is that it does not need to set the hyperparameters extensively, only the number of trees must be set. Random forest is restricted to only tabular format data, which lower the usage of the algorithm, unlike neural networks, which can handle tabular format, images, speech, and text. Boosting is an ensemble method that improves the prediction of weakly learned models iteratively. Boosting works similar to bagging, except that the trees are grown slowly and sequentially from previously grown trees. Here, each tree is fitted using the predicted output of the previous decision tree rather than the actual outputs. AdaBoost 542 is the first boosting algorithm developed for binary classification, which uses one-level decision tree with one node and two leaves, also called as decision stumps. Here, every NV data are given sample weight. During the start of training, the sample weights, W, are initialized as for each NV. These weights for each sample determine the importance for correct classification. The weighted samples always sum up to 1. The total performance of the algorithm is calculated using the below formula, 64, where E is the total number of misclassifications. In AdaBoost, more weights are assigned to incorrectly classified samples so as to correctly classify in the next decision stump, and low weight are assigned to correctly classified. We perform the above step until we achieve the best accuracy or maximum iterations have been reached. After finding the performance of the model, we update the sample weights as follows: 65, where for correctly classified data we update the current weight with previous weights times the Euler S number raised to a, and for incorrectly classified data we update the current weight with previous weights times the Euler S number raised to plus a.
Here, we penalize the weights that are correctly classified.
The final discriminant for K classifiers is 66, where components DIC, X, are hardened, algorithm 8.
Algorithm 8 AdaBoost. Given D equals XP, IC, P equals 1 to NV, K classifiers / estimators 2. WK, P, is proportional to P, pattern P being chosen. 3, for K equals 1 to K do 4, create dataset DK by sampling D according to WSK, P, and train weak learner, classifier, CK on set DK 5, calculate total error, E, using EQ, 646. Update the weights for correctly classified data by using E in equation if XP classified correctly by CK alone. 7. Update the weights for misclassified data by using plus E in EQ, 66, 8, and for from a programmer's perspective, 1. In scikit-learn library in Python, the base estimator for approximation and classification is a decision tree. AdaBoost can also give us which features are important. In scikit-learn library, AdaBoost classifiers decision tree maximum depth by default is 1, but in AdaBoost approximation, the default is 3. AdaBoost is prone to overfitting. Gradient boosting 43, is a method that uses negative gradient descent as part of a prediction matrix. As we saw in AdaBoost, the weights are initialized equally. After the first training set, more weights were assigned to the observations that did not classify successfully, and less weight was assigned to the observations classified successfully. These adjusted weights are used for training the next decision tree. However, in gradient boosting, the weak estimators are fitted on the residual error of the previous decision tree. Therefore, it focuses on the difference between the original and the predicted output. Using the error function defined in EQ, we find the incorrectly predicted class by our model. We find a negative gradient with respect to the loss function for those incorrectly predicted classes as follows: 67, where 11 is the incorrectly predicted patterns. We built a new model based on the gradient values as the predictors. We do the same process for a certain number of iterations. The final prediction is the weighted sum average of all the predicted models, algorithm 9. Algorithm 9 gradient boosting. Given D equals XP, IC, P equals 1 to NV, K classifiers / estimators 2, calculate the predicted output, 68, 3, calculate the residuals as follows: 69, for fork equals 1 to 5, construct a decision tree with inputs as XP and outputs as RESP6, predict the new target YP using all the decision trees using below formula. 77, calculate the new residuals 8, and for from a programmer's perspective, 1, a different loss function can be used according to the classification or approximation needs. The learning factor is a hyperparameter used to predict new variables as a small value, usually. Gradient boosting works well when we have unbalanced class data. Gradient boosting is not a good choice if there is a lot of noise in the data and can tend to overfit. Boosting methods are outlier sensitive as it depends on solving the previous errors. Boosting is impossible to scale as every predictor strongly depends on the previous predictor's error. Chapter 2: Supervised Learning, From Theory to Applications. Ashish Tiwari Masters in Computer Applications, Jamia Millia Islamia University, New Delhi, India. Abstract supervised learning is one of the most important components of machine learning, which deals with the theory and applications of algorithms that can discover patterns in data when provided with existing independent and dependent factors to predict the future values of dependent factors. Supervised learning is a broadly used machine learning methodology with its applications in diverse areas like natural language processing, image and video classification, medical analysis, and many other prevailing fields. This chapter explains various supervised machine learning techniques, and a single chapter may not be adequate for a complete review of the same. Nevertheless,
we hope to cover the key issues and state of the art for suggesting researchers regarding their research directions and stating possible setbacks that have yet to be explored. In the preliminary section of this chapter, we will present the basic concepts behind supervised learning with some examples to comprehend the idea, followed by different types of supervised learning problems. Researchers have proposed a variety of techniques to solve such problems, like instance-based techniques, logic-based techniques, stochastic techniques, and so on. Consequently, the middle section of this chapter will discuss some commonly used algorithms of supervised learning and their efficacy in terms of complexity, accuracy, overfitting risk measures, and speed of learning. To investigate the robustness of the model, it is important to evaluate the results, and that's where we will discuss evaluation metrics like accuracy, precision, recall, etc., along with main problems encountered while making our model learn. At last, we will look into the wide areas like computer vision and text media that exploit techniques from supervised learning. Keywords: supervised learning, regression, decision trees, evaluation metrics, computer vision, NLP. Introduction. Machine learning is an application of artificial intelligence in which intelligence is provided to a system so that it can act automatically and make decisions depending on the past experiences. Machine learning has provided us ability to recognize images, analyze speech or audio data, hate speech identification in texts, and even self-driving cars. The recommendations shown to you on Netflix and Amazon, virtual personal assistants like Alexa and Siri, are some of the day-to-day applications of machine learning. Machine learning methods/algorithms are categorized in two main parts: supervised learning. Supervised machine learning is the most famous and most common type of machine learning. Supervised machine learning refers to the art of learning with example. We can recognize a book because someone, sometime in past, taught us that this collection of digitally typed papers bonded together with a hard cover on the top, and the bottom is a book. Since then, we can recognize a book when we see one. That's what supervised learning is: learning by careful consideration of different features of an object provided with the label of that object. The features are the key component for the identification of the object. If an object matches all the features of a book described above apart from one feature that it does not contain digitally printed text or any text at all, will it still be called a book? The features help us accurately identify the class of the object. The better the features are, the more accurate your predictions are going to be. Supervised learning is a technique, and it is used in machine learning with the help of certain algorithms that implement supervised learning in different ways. Classification and regression are two types of supervised learning, in which former deals with the process of assigning a category to each observation from a predefined set of categories, and later is a technique used where the output is continuous in nature, like monthly salary or total sales on a day. Unsupervised learning. This method is used when the data provided to train is neither classified nor labeled. Unsupervised machine learning algorithms try to infer a function to find hidden relations between data points. Since there are no labels while training, the algorithm does not focus on the right output. Instead, it focuses more on exploring the data to identify hidden patterns. K-means clustering is one of the most used unsupervised learning techniques to divide the data into clusters of similar attributes. In this chapter, we will understand and explore the domain of supervised learning in detail, along with the steps to apply supervised learning to real-life data to obtain accurate results. What are regression and classification problems? To understand them in a better way, let's first learn the common terminology used in the world of predictive modeling. The above table contains sample data having a unique identifier, car ID, for each observation, 3 independent variables, namely no of seats, mileage, and top speed, and an independent variable price, which is our target to predict. We will call it target variable. Independent variables: the variables or features in the provided data which may or may not depend on any other feature. Technically, there are possibilities that one or more independent variables are correlated, and this correlation plays an important role in understanding the relationship between different independent variables and eliminating redundant factors. Dependent variable, the target variable, whose value is to be determined using independent features. The target variable may be dependent on all independent variables or some of them. Mostly the case is that some of the independent variables have more effect on dependent variables than others. R-square and adjusted R-square test are a few of the most famous statistical measurements of the variance of the dependent variable that is explained by independent variables. In Table 1, the target variable is price, which is a large number having minimum value of 800,000 and maximum value of 2 million. For more data, the variance in both independent and dependent variable will be more. The target variable can go as low as 50,000 to as high as 10 million. Such types of problems, in which target variable can have any value from a minimum value to a maximum value, are referred as regression problems. Sample data for regression problem. Car ID know of seats mileage top speed price. C4. For 180 800,000 now, if instead of price as target variable we add class as target variable, as shown in Table 2. Sample data for classification problem. Car ID know of seats mileage top speed class. Adhere target variable is class, which might be representing the category of the car, like if it's a SUV or sports car, etc., and will have definite number of predefined categories. From Table 2 we can see that there are two categories of cars. This kind of problem where target variable can be assigned only one of the category from predefined set of classes is referred as categorical problem. Figs 1 and 2 gives pictorial representation of the two supervised learning problems we discussed. Fig 1 diagrammatic representation of classification problem. Fig 2 diagrammatic representation of regression problem. Fig 1 represents a classification problem in which the model, the straight line, is able to classify the two classes clearly. The triangles and ovals in the diagram are data points, independent variables. Don't get the wrong idea due to the difference in shape in the diagram. Unless classified properly, they all are the same thing, data points. Let us just assume they all were square before being classified. Then we trained our model on trained data, and the model was able to identify triangles and ovals separately. Fig 2 represents the regression problem in which the target is to predict the target value so that it aligns with the regression line. In Fig 2 the relationship is shown between only two variables where y-axis represents the target variable and the x-axis represents the independent variable. If there were more than one independent variable, which is generally the case, this representation will have more axes and it will have n dimensions, where n is the number of independent variables with a straight line in between representing the target regression line. Learning algorithms. Machine learning algorithms are the main brains behind learning magic and making predictions. Each algorithm is just like any other programmed code which works according to logic. The same base algorithm can be used to perform both regression and classifier tasks using different versions of it. First, we will discuss the regression algorithm. Don't confuse regression used in the context of an algorithm with that of a problem. A regression problem is a category of machine learning problems, whereas a regression algorithm can be used to solve both classification and regression by just tweaking the output generating step a little. The other algorithm we are going to talk about is a tree-based algorithm like a decision tree. Linear regression. A linear regression algorithm attempts to establish relationship between independent variables, x, and dependent variable, y, by fitting a linear equation to the observed data, 1.
A linear regression line has an equation of the form y equals a plus bx. The slope of the line is b, and a is the intercept, the value of y when x equals 0. X here can represent a single variable or a set of features that collectively can determine y. From Table 1 we can say that x equals no of seats, mileage, top speed, and y equals price. The aim during training is to minimize the value of cost function which is proportional to YPE2, where YP is the predicted value by algorithm for an observation and E is actual value of target variable for its observation for some fixed value of A and B. Average cost value is calculated at the end of one full training over all the observations and value of A and B is updated subsequently. The update value of A and B is used for next run. This training process ends when algorithm find an optimal value of A and B which yields least cost and hence most accurate results. Logistic regression is a linear regression model with a modified equation for dependent variable used for classification problems. A sample equation for logistic regression looks like y equals e, a plus bx, / 1 plus e, a plus bx, 2, where x or is that we discussed in but y which is our dependent variable or target variable is now a probability. For binary class classification problems, where possible outcomes can be converted to 0 or 1, the logistic regression predicts the probability of an observation belonging to class 1. While implementing the same in Python, we can make use of predefined functions to either get probability as output or the exact class itself. Decision tree is another important machine learning algorithm, variations of which are used widely by the practitioners. To understand how decision tree works, we need to understand few terms associated with it. Entropy, it is a measure of the uncertainty in the possible outcomes of a variable from a sample. 3. Entropy is calculated using the formula H(x) equals I equals 0 NP 11 log 2p 11, where n number possible values x can have. Information gain, it is a measurement of purity or homogeneity in a data sample. 4. A feature with more information gain is considered more informative in terms of target prediction. Information gain is given by entropy of the target variable, entropy before split, entropy of the target variable in respect to an input variable, entropy after split. Where H(s) denotes entropy of target variable before split, H(c) denotes entropy of if partition of S, G, S(a) denotes the information gain for set of training examples S of feature A. To construct a decision tree, we will calculate information gain for each feature, and the feature for which we obtain maximum information gain is chosen as the root node of the tree and first split is performed. This process is repeated for each split of root node, which leads to formation of further nodes. Same process is repeated for each split unless we are left with only leaf nodes. Decision trees can also be used for both classification and regression problems. Fig. 3 gives diagrammatic representation of a decision tree for data samples from Table 2. Fig. 3 sample decision tree for data in Table 2. There are numerous machine learning algorithms, each having its own advantages. One important thing to note is that different problems can have a different best fitting model. No algorithm is good for all problem statements, although practitioners have their favorite models that they prefer to start and work with. Variants of decision trees such as random forest, XGB model, etc. are widely used algorithms in the field of machine learning. One trick to find out which model will fit best on the data is to try different models on data after pre-processing and finally choose the model with the best results. If there are 2 or more best models with close performance, fine-tune the models and choose the one which gives the best accuracy. Linear models can be imported in Python using sklearn_s linear_model library, and tree models can be imported using tree library. To use variants of tree-based models, use sklearn_s ensemble library.
Evaluation metrics. To measure the quality of the machine learning model, we need to validate its output using an evaluation metric. One of the most important steps in supervised machine learning is to choose an appropriate evaluation metric for the problem at hand. Now, just like we have different algorithms for classification and regression problems, we also have various evaluation metrics too. Choice of evaluation metrics also depends on the problem at hand, and in most cases, evaluation metrics can be determined by going through the problem statement, unlike choosing the algorithm to solve the problem. Few of the most commonly used evaluation metrics for regression problems are R-square, adjusted R-square, mean square error, and root mean square error, and for classification problems most commonly used metrics are accuracy, F1 score, AUC-ROC, for binary classification only, recall and precision. Confusion matrix is another important metric for classification problems that gives a visual representation of model classifications. All of these metrics are available in Sklearn Metrics library and are very easy to use. Let us have a better understanding of few metrics that we will be using in this chapter. Mean square error. MSE helps in evaluating different regression model on a data set and hence helps in deciding the best fitting model for the problem. MSE is calculated using formula where E is the actual value of target variable for data instance I, YP is the predicted value for that instance by the model. Square of difference of E and YP is added for each data instance, and then its mean is calculated by dividing it by n, the number of total instances. We will use the data present in Table 3 for better understanding. Here YP column contains the value predicted by our model and EYP2 is a calculated square difference. As it is evident from the data, the square difference is much larger than predicted and actual values. Squaring the difference translates the negative differences to positive, hence an error will always add up while calculating the total error. On taking the sum of the square difference and dividing it by the number of observations, which is 5 in this case, we get 164,482,000. This is our mean square error. The value of MSE can be very large when the target variable has a high value. The higher the value we are trying to predict, the larger will be the square error, as no model is perfect and there will always be errors. Square error between predicted and actual values. YP, EYP, 254,000, 50,000, 16,000,000, 36,000, 40,000, 16,000,000, 40,000, 460,000, 384,000,000, 160,000, 100,000, 82,000, 500, 306,000,000, 250,000, 120,000, 110,000, 100,000,000. Root mean square error, another important metric for regression problems. Simply put, RMSE is the square root of MSE. As we observed in section, MSE is very high when the target variable contains large values. To represent results with such a huge error will leave a negative impression on the target audience, as it seems the model did a very bad job. Though the observations aren't that bad, our model predicted 54,000 for a target of 50,000, which is close. But that is not the only factor because of which one should choose RMSE over MSE. This is generally decided based on the characteristics of the data during the initial planning. Both RMSE and MSE are used for regression problems. Confusion matrix. A confusion matrix represents the prediction summary in matrix form. It shows how many predictions are correct and incorrect per class. It helps in understanding the classes that are being confused by model as other class. Fig. 4 shows a sample confusion matrix. 5 for binary classification problem. Fig. For confusion matrix. TP here stands for true positive predictions. For a binary classification problem like classifying the fraudulent transactions as 1, TP will give the count of the number of 1s that were correctly classified as 1, i.e., number of fraudulent transactions that were classified as fraudulent.
TN stands for true negative predictions, a number of 0s, non-fraudulent transactions, classified as 0. FP, false positive, is the count of number of non-fraudulent transactions that were classified as fraudulent, and FN, false negative, is the count of number of fraudulent transactions that were classified as non-fraudulent. Accuracy is calculated by counting number of correct predictions made by the model out of total predictions, from Fig. For accuracy can be calculated as accuracy is the most commonly used classification metric for balanced dataset. A balanced dataset is one in which the target variable consists of classes in the same or almost the same ratio. An unbalanced dataset will have the majority of data points belonging to one category and very few to other categories. Accuracy should not be used with unbalanced dataset, as a model trained on such a dataset will have high predictions for the majority class and hence high accuracy. Let us consider a case where we are provided with images of brain scans and are supposed to detect the tumor in the brain, and the class ratio is 1 to 100, where only 1 out of 100 scans have a positive response to the tumor. In such cases, even if the model predicts few positives as negative, accuracy will still be high because most of the predictions will be correct as they belong to the majority class, and this might give the satisfaction of having a well-fitted model and hand through the model as risking people's life by classifying the positive case as negative. In such cases, we need a metric that focuses more on false negative, FN, rather than overall accuracy. Recall is one of the most suitable evaluation metric to use while dealing with imbalanced data for the cases where we want low false negative rate, like that in the tumor example discussed in section. Recall is calculated by the formula. From the formula, it is quite apparent that recall will be higher when predictions contain a very low false negative rate. The higher recall will provide more confidence in classification results of the model. Precision is the measurement of how precise the model is in terms of positive predictions. Precision is calculated as the ratio to true positive to the total positive, TP plus FP, predicted by the model. Precision is better suited for the cases where we want more confidence in our positive outcomes. Let's say we are provided with data to detect possible cheating attempts by candidates while appearing for university examination online. Just for heads up, when provided with appropriate data, any problem can be solved using supervised machine learning. For this problem statement, we could be provided with the number of times the student tried to switch browser tab or the duration for which candidate was not facing the system screen, etc. Any positive claim about a student can ruin his/her semester efforts, and hence we need to be careful regarding our classification predictions. You should be able to figure out now what possible classes, in this case, will be. For such a problem, precision is a better metric to evaluate with. F1 score. Mathematically, F1 score is defined as the harmonic mean of recall, R, and precision, P. F1 score punishes both low recall and low precision, so even if we have high recall but low precision, F1 will still be low. Suppose our model gives precision and recall for fingerprint recognition system. F1 score for which will be equals. It can be said that F1 score maintains a balance between recall and precision. 6. So we have an idea about different supervised learning problem categories, basic algorithms, and their working and evaluation metrics which are used to judge the performance of our models. One of the common attributes that are shared by models and metrics is that their choice highly depends on the problem at hand. The first step in solving a machine learning problem deals with the understanding of the problem, because failing to do so can result in the selection of the wrong model and metric, and no wrong model can provide good accuracy. Let us apply our knowledge on some real-life datasets. Supervised learning to detect fraudulent credit card transactions. Detecting a fraudulent transaction is still a big challenge, as it only takes few seconds for a transaction to be completed.
In this section, we will build a model on an open-source dataset to classify fraud transactions from genuine transactions. We will use Python and Jupyter Notebook to write and run our code. The data provided, 7, is obtained after reducing the number of columns to 30 by applying Principal Component Analysis, PCA. A real-life data can have huge numbers of columns where each column represents a different dimension. PCA helps in reducing the number of columns by performing simple matrix operations to calculate a projection of the original data into the same or fewer number of dimensions. Column names are anonymized, V1 V28, due to confidentiality issues. Hence, we will judge a column by the values it contains instead of its name.
Data exploration: download and extract the CSV file from the data link, https://www.kaggle.com/mlgulb/credit card fraud. Read the extracted CSV file in a data frame, DF, using read_CSV utility of Pandas library. We will begin by getting a basic overview of the data. DF shape will show the dimension of the data frame.
It contains 284,807 rows and 31 columns, including target. Class is our target column with two categories: 0 for non-fraudulent transactions and 1 for fraudulent transactions.
The time column is not in datetime format but float instead.
Since data is only of 2 days, it appears the time column is converted to seconds from the start of the day instead of actual time.
DF
describe will show some descriptive statistics like mean, min, max, etc. of each column. Only time and amount column are in their original from rest contain values resulted after PCA. From Fig. 5 we can see that the amount column is highly right-skewed and contains few observations with large values as compared to other observations. Fig. 5 distribution plot for amount has a long tail on right side. This is a classification problem as there are only 2 possible outcomes. Also, one of the peculiar thing about the data is that the number of observations with classes 1, 492, is very less as compared to the number of observations with classes 0, 284,315. As already explained in section, this is an unbalanced data problem. Data pre-processing: we will normalize the amount and time column before feeding the data to the model. For tree-based algorithms, normalizations doesn't have significant impact, but for regression-based algorithm it does, as each attribute is multiplied with a coefficient. If values are not normalized before model fitting, a column like salary with higher variation in values can have more influence over the prediction than other columns that have low variations like age. This can be easily done using standard scalar or min-max scalar functionality provided by Sklearn's pre-processing package. It is always advised to make a copy of data frame and perform pre-processing on the copy instead of the original data frame so that we can always look at original data for any analysis during the whole process. Below is the code segment to achieve the same. From Sklearn. Pre-processing: import standard scalar. df_copy equals df. Copy, scalar equals standard scalar, df_copy, amount equals scalar. Fit_transform, df_copy, amount. Values. Reshape, 1 df_copy, time equals scalar. Fit_transform, df_copy, time. That is the heart of artificial intelligence and machine learning for edge computing. If it helped, a quick subscribe keeps more summaries coming. So how do learning and algorithm connect? That is exactly where we started. Go back to the top and watch it click into place.